For 30 years, the contract between software engineers and their deployment pipelines has been elegantly simple. You feed a function a known input, you get a deterministic output. If those two values match, the build is green. This binary pass-fail assertion became the bedrock of the modern internet. It allowed e-commerce platforms and streaming services to scale because the underlying software followed predictable, repeatable logic. Agentic AI obliterates that contract. An autonomous agent doesn't just compute, it plans. It accesses memory, invokes tools, and adapts mid-flight, based on API latency or the content of retrieved documents. This means if you give the same agent the same prompt twice, you can get two entirely different execution paths. Both paths can be correct, yet they look nothing alike to a traditional test. Applying static unit tests to these non-deterministic systems is a mismatch in logic. When you use binary assertions to verify an agent, you are shipping unverified autonomy into production. We see this failure pattern repeatedly. Developers write test suites that pass on deterministic mocks, only to watch the agent fail in production. The mocks were lying, and the assertions were checking the wrong thing. Final output assertions measure the shadow on the wall, not the fire casting it. They verify that a result was reached, but they ignore the reasoning that created it. To solve this, the enterprise must move from testing outcomes to evaluating trajectories. A trajectory is the complete path the agent takes, the reasoning chains, the memory updates, the decision branches, and the exact parameters used in every tool call. In regulated enterprise environments, this testing gap represents an existential risk. Relying on final outputs to verify autonomous agents introduces a liability no compliance team can accept. This risk is most visible in generative UI or Gen UI. Instead of using pre-built dashboards, agents now invent bespoke interfaces at runtime, tailored specifically to the user's query and screen size. Legacy tools fail in this environment because they expect a static DOM. In Gen UI, elements are invented instantly, leaving traditional test selectors chasing ghosts. Many teams try to solve this by forcing agents to produce static, predictable layouts. This defeats the purpose of autonomy, turning a sophisticated agent into an expensive, rigid dashboard generator. First, validate the structural contract. Test the underlying semantic JSON payload to verify data is correct, regardless of the UI display. Second, use visual language models as an automated human proxy to confirm the visualization accurately fulfills the user's intent. Testing Gen UI with static scripts is like demanding a drone fly on train tracks. We must validate what the interface communicates, not the specific coordinates of its pixels. Consider a CloudOps agent instructed to resize a production database from 8 to 16 vCPUs. The task completes, the database is resized, and the test marks it as a success. However, the agent actually paused mid-execution because it detected an active database backup. It waited 10 minutes to avoid corruption, but the test suite never verified that this reasoning was correct or even occurred. Task completion testing ignores hidden variables. It cannot tell if the agent misinterpreted a log or skipped a snapshot. Solving this requires grading the trace across 4 pillars: LLM reasoning quality, memory state updates, tool exactness, and environment feedback interpretation. While capturing these traces is easy, scoring them manually is impossible at scale. Multi-agent evaluation architectures can now score these trajectories automatically, providing a full audit of the agent's logic in seconds. Relying on task completion is like hiring a chauffeur who runs red lights but still reaches the destination. In an enterprise setting, the successful arrival is a liability if the journey was reckless. In tool execution, the stakes are financial. Imagine a procurement agent that queries a vendor API and receives a clean 200 OK response. It summarizes the results, and the CFO approves a $2 million contract based on that analysis. Weeks later, you realize the API was paginated. The agent only read the first 15 records and missed the cheaper vendor on page 3. The tool call was syntactically perfect, but the agent didn't know what it didn't know. Static mocks failed to patch this because they encode the developer's own blind spots. If the developer didn't mock pagination, the test will never verify that the agent can handle it. Golden trajectories replace static mocks, capture real production traces, then mutate them with fault injection. simulating rate limits or high latency. This forces the agent to exercise error recovery logic, testing against messy, real-world data. Testing against perfect mocks is like shadowboxing in a mirror. You look perfect until you get to production and reality finally punches back. Learning agents present a unique challenge. They change over time. A coding assistant might write perfectly secure, compliant code on its first day of deployment. By day 30, after absorbing weeks of opinionated feedback from a tech lead, the agent's style has evolved. It now generates code that matches the lead's preferences, but violates global enterprise security standards. This drift happens gradually. Because an agent's behavior is a function of its accumulated memory, a test that passes on day 1 will fail on day 30, even if the core code hasn't changed. This requires continuous behavioral monitoring. You must run living golden datasets against the agent's current memory state on a weekly cadence to detect these shifts. We use an agent as a judge framework to handle this evaluation. A grader scores the output against a rubric. A critic challenges that score for missed edge cases, and a defender prevents the evaluation from becoming over-penalizing. Memory drift is continuous, so your monitoring must be too. An agent's correctness is not a permanent state. It is a temporary condition that must be re-verified every week. The most common objection to this level of testing is that LLM-based evaluation is too slow and expensive for a standard CI/CD pipeline. This is no longer true. Local, fine-tuned 7 billion parameter models can now score complex trajectories in under 500 milliseconds. The cost of this evaluation is negligible compared to the cost of a production failure. We must also stop relying on underlying model benchmarks like MMLU as a proxy for system safety. Catastrophic failures happen in the gaps between the model and the environment, when retrieval returns stale documents or tool calls truncate critical parameters. The model is merely the engine. Benchmarking it tells you the engine is powerful, but it doesn't tell you if the car can stay on the road. You have to test the integrated system. Do not wait for a perfect QA pipeline. Build a minimal viable eval harness this week to get immediate signal on your agent's behavior. Start by capturing 5 golden trajectories from your staging environment. Log every prompt, tool call, and reasoning step to create your baseline. Define a basic rubric for what good looks like across the 4 pillars and wire it to a simple multi-agent evaluation framework. Automate a weekly regression run against the agent's memory. If a trajectory deviates, a tool call is missed, or reasoning fails, trigger an immediate alert. These 5 trajectories provide a safety net, catching silent tool failures and reasoning drift that manual testing misses. Rigorous trajectory evaluation is the only shield preventing autonomous systems from triggering a production disaster. You must evaluate your agents before your customers do.